Okay, so today we'll discuss about the Wheatstone Bridge. So the Wheatstone Bridge will use means the Kirchhoff's law here, Kirchhoff's rules, that is Junction Rule and the Loop Rule here in the Wheatstone Bridge, the calculation of the Wheatstone Bridge. So today we'll discuss about Wheatstone Bridge. Wheatstone Bridge. So in Wheatstone Bridge, we'll connect four registers in this pattern. Four registers are connected and we'll connect with a battery or cell, and let's say we'll have some voltage or it's a source voltage, some EMF. Now there are four registers here. Let's say this is R2, this is R1, this is R3, and this is up. Okay, R1 and R2 both are fixed registers. R4 is the unknown one. We'll calculate the value of R4 from these combinations. So R4 is the unknown one, and R3 will adjust R3. R3 is a variable resistor, standard one, or will change R3. It's a variable. It's a variable one. Will vary R3 so that why will vary R3? Will vary R3 so that means they will be in a balanced condition. Balanced condition means if I will join one galvanometer, then the galvanometer will show no deflection or zero deflection. Okay, if the galvanometer will show zero deflection, that means what? That means the current flowing through this galvanometer Ig will replace it. Ig is equal to 0. So in such condition, that when the galvanometer will show no deflection or zero deflection, in that case what will say? Will say that it's in the balanced condition. That means R1, R2 and R3, R4, these are in the balanced condition. So using this condition and using the case of your Kirchhoff's rules, using the Kirchhoff's rules, we will calculate the unknown resistor from this combinations or this type of your diagrams. So here, as I told you, R1 and R2 are the known resistors, R3 is a variable resistor, and R4 we do not know the value of R4. So we'll adjust in R3 in such a way that the current through this galvanometer on this arm will be 0. Then no current will flow through this arm, or the galvanometer will show no deflection. So how will you proceed? So we will proceed using the Kirchhoff's rules. As you know, the Kirchhoff's rule, two rules are there. One is junction rule, another is loop rule. So we'll use here, suppose as it is a EMF, so current will flow in this way from positive to negative as a conventional current. So here, let's say through this resistor R2 the current I2 is flowing, and through R1 the current I1 is flowing. Similarly, through resistor R3 or through this branch the current I3 is flowing, and through this unknown or this arm through this unknown resistor this current, let's say I4, is flowing. Okay. And in balanced condition the current Ig will be 0 through this arm. So as you know from Kirchhoff's junction rule, that is the sum of all incoming current must be equal to sum of all outgoing current, and the loop rule, that is the important rule that we will use here, that is the changes of the potential across the resistors and the cells in a loop is 0. So let's say we'll proceed in this way, we'll move in this way. Okay, so when we'll move in this way, we are getting a resistor on our way. So how will you write it, this equation? So the changes in potential, so what the potential, how much potential will be changed, uh, will be here, how much potential drop will be across this R1 resistor. So this R1 resistor, as we are moving in the direction of the current, so the potential difference or drop will be V is equal to IR. So from there, this equation, the potential drop will be I1 R1. Okay, now we'll move, and in this direction will move, but here Is is equal to 0, so no current is flowing in the balance condition. No current is flowing through this galvanometer, through this branch, so this will be Iz into R is equal to 0. Iz is 0, so plus 0. Now we'll move and we'll proceed in this direction. So now in this branch, that is the R2, the resistor R2 branch, in that branch we will face the opposite current. So as I told you, when we will face the opposite current, we will write plus. So this is I2 R2. So the changes of the potential across resistors and cells in the loop, this is a loop, is equal to 0. This is the Kirchhoff's law. Okay, so this equation we got. Now this is suppose equation 1. Now let us write the equation, another equation for the second loop. Let's take the second loop. So in the second loop, let's say we'll move in this way. So when we'll move in this way, the current direction is this one, I3. So we are moving along the direction in this branch, in this through this resistor R3. So I'll write minus I3 R3, right, and I'll meet the current against it in through this R4. The current direction is this direction, but I am moving in opposite, okay, in this loop. So here I'll write plus I4 R4, and again when I'll move through IZ, no current through IZ, so I'll write plus 0 is equal to 0. So now you can see we got two equations here, and another using the Kirchhoff's junction rule, we will write here that here this one I2 is flowing. Now as Iz is 0, so Iz plus R4, this is outgoing, incoming is I2, so I2 will be equal to, using the junction rule, I2 will be equal to Iz plus I4. As Iz is equal to 0, so we can write that I2 is equal to I4. Similarly, we can write I1 is equal to I3. I1 is equal to I3. Okay, so let us erase thing. Okay, so now what are the equations I have now with me? So I have with me, you can see, okay, one is minus I1 R1 plus I2 R2 is equal to 0. The second one is minus I3 R3 plus I4 R4 is equal to 0. And we got also this relationship, that is I1 is equal to I3, and we also got I2 is equal to I4. Now we'll replace this I4 and I here, I3 and I4 here. So we'll get the equation I3 R3 is equal to I3 is equal to I1, not R. We'll replace this I3 and I4. So I3 is equal to I1, I3 is equal to, so minus I1 R3 plus I4 R4, I4 is I2, I2 R4 is equal to 0. Now let me rearrange the left side. So now this is suppose equation 1, this is equation 2. So if I'll write it, I will get like this, that is I2 R2, I2 R2 is equal to I1 R1, or I can write R1 by R2 is equal to I2 by I1. So this is one relationship I will get from equation 1. Similarly, from equation, this second equation, what I can get is I can write this one, I2 R4 is equal to this one, I2 R4 is equal to I1 R3, or you will write like this, or you will write that your I2 R4 by R3 is equal to, or you will write like this, R3 by R4 cross multiplication, R3 by R4 is equal to I2 by I1. So let's say this is equation number 4, this is equation number 3. So from 3 and 4 you can see the right hand side is equal, so the left hand side must be equal, that we can write from equation 3 and 4 we can write that R1 by R2 is equal to R3 by R4. This is the relationship between the resistors in the Wheatstone bridge. So from here we can calculate what is the target of the Wheatstone bridge. We can calculate the unknown resistance R4, and this Wheatstone bridge, this is a practical device, and this principle is used in meter bridge. Okay, this Wheatstone bridge technique is used in the meter bridge, which we will discuss in the later class. So here you can calculate, we have taken R4 as the unknown resistor, so here you can calculate the unknown resistor R4, that you will calculate like this, So the unknown resistors will be R4. So R4 is equal to R4 is equal to R4 is equal to R3 into R2 by R1. So the relationship you remember that R1 by R2 is equal to R3 by R4, or you can say R2 by R1 is equal to R4 by R3. So this is the relationship, and we can calculate the unknown resistor, the value of the unknown resistor from this relationship. And as I told you, it has application in meter bridge. Okay, so in the next class we will solve some questions based on the Wheatstone Bridge, and of course the application of Kirchhoff's law, and also we'll discuss about the meter bridge. Thank you.